Okay, so imagine you're air traffic controller, okay, of an international airport. Okay, so most international airports are actually very busy, right? So at any one time, you have lots of airplanes coming in, landing and taking off, okay, in the airport. And most international airports, they can't simultaneously handle all the airplanes coming in, right, or taking off. So you need some way to schedule the airplanes, right? Correct. So that's basically the job of the air traffic controller, okay, to schedule when the planes come in, when the planes land. Okay, so if you are the air traffic controller, or you are sort of the programmer who writes the program to schedule the airplane, okay, so what is the best data structure to use that you know of? A queue, right? Correct. A queue would be a good data structure, right? So the one who should land first will be at the front of the queue. The one who should land last is at the back of the queue, correct? Yeah, so a queue data structure is good. Okay, so imagine now you are air traffic controller. Okay, so you have scheduled 2 aircraft to land, X and Y. Okay, so X will land in the next 3 minutes, so it's at the head of the queue. Okay, and then aircraft Y will land in the next 6 minutes, so it's the next one in the queue. Okay, both have enough fuel for at least the next 15 minutes, and both are just 2 minutes away from the airport. Okay. So next few slides are hidden, okay, not in the slides given to you. So 2 options are presented to you. Raise and wave your hand if you choose option 1. Raise and do not wave if you choose option 2, okay, after I show you the next slide. Okay, so you must decide very fast. Okay, you cannot think. Okay, now suddenly you receive SOS message. Okay, aircraft Z is running out of fuel, request to land soon. Okay, and the pilot of this aircraft estimates he only has 3 minutes of flying time, approximately 3 minutes away from airport. So what do you do? Okay, option 1. Raise, wave your hand. Okay, option 2, stick with it. Raise your hand, raise your hand. Oh, one guy at the back, raise his hand. Okay, if that guy at the back is the is the air traffic controller, right, this is what's going to happen. Okay, so this is an actual tragedy that occurred because the air traffic controller had a miscommunication with the pilot of this aircraft. He thought that they had enough fuel to last, okay, longer, so they didn't allow the airplane to land first. Okay, so this is what happened. Okay, so now, oops. It's okay. So yeah. So you should actually let aircraft Z land first, lah. Okay. Now, if you were using a normal queue, right? Can you do this? You have already slotted aircrafts in the queue already. So the next aircraft that's going to come in is at the back of the queue, right? So you cannot actually change a priority of the new aircraft coming in so as to put them at the head of the queue. Okay, if it's a normal queue. Yeah. But here you need to do that, otherwise tragedy will happen, correct? So, I mean, if you think about it, in a normal queue, yes, you shouldn't allow people to just jump queue, correct? If you are in a taxi stand here and lots of people, then you try to just go to the head of the queue, what's going to happen? What's going to happen? You'll be wet, okay? So you shouldn't do that, but in this kind of case, you need to be able to make this kind of priority change. Okay. Obviously, if you use a normal queue, that's not sufficient. Okay, that's not sufficient. Okay, so what you need is basically a new kind of abstract data type called a priority queue. Okay, where the items are actually ordered according to their priority. Okay, according to their priority, and then you take them out according to the priority. Yeah. Okay. Okay, so let me introduce this one. The abstract data type, priority queue. Okay, so like a normal queue, there are just 2 very basic operations that you need. Okay, one is called enqueue, one is called dequeue. Okay, so you enqueue an item X into the priority queue in some order based on their priority. Okay, so the priority is basically the key value, okay, that is used when you insert something into a priority queue. Okay, next, dequeue is to return the item Y that has the highest priority or key value from your priority queue. Okay? And then if there are more than one item with the same highest priority, right, then you just return the one that's inserted first. Okay, so this will be like a normal queue, first in, first out. Okay, when they have the same highest priority. Okay, so usually, okay, we define higher priority to be a higher number. We usually use a numeric number to represent the priority. Okay, but depending on the application, sometimes a higher priority can be represented by a lower number instead. Okay, so it depends on the application. Okay. Right. Okay, just to revise a little bit, what's the data structure? Okay, so data structure, way to store, organize data to support efficient operations on the data like insertion, searches, deletion, queries, updates. Okay, and the more important thing is this, that I want you all to take note of, is most data structures have some property they need to maintain. Okay, yeah. So, okay, just using your 10-20 knowledge, now you know that, oh, I need a priority queue instead of a normal queue, right? How will you implement your priority queue? Just using your 10-20 knowledge, what you know now. Yeah, show you. One way to do it using 10-20 knowledge is to use a circular array-based implementation of your priority queue. Yeah. So there's a property that needs to be maintained in this implementation. Okay, that is the content of your circular array, right, is always in the correct order, meaning that the one of the highest priority is always at the head of the queue. Okay, the one of the lowest priority at the back of the queue. So you can imagine that they are sort of in sorted order according to their priority, lah. Yeah. Okay, so imagine now I have this priority queue. Okay, all I need is basically in this circular array-based implementation, I need two pointers, right? One is the front pointer pointing to the front of the queue. One is the back pointer pointing to the back of the queue. Yeah. So at the beginning, okay, I have only two aircraft. Okay, using my example. Okay, aircraft X and aircraft Y. So aircraft X is at the front. Okay, aircraft Y is at the back. Okay. Okay. Next, when you enqueue, okay, I need to find the correct insertion point because that's the property I want to maintain. Correct? Everything is always in correct order. Okay, so now I have a new aircraft coming in, aircraft Z. Okay, where should I insert it? If it's normal queue, I just insert it at the back, correct? Advance my back pointer by one and then insert at the back. Okay, but in this case, aircraft Z, highest priority, right? It needs to go all the way to the front of the queue, correct? So what do? You advance your back pointer and then, like how you do insertion sort, right? You start moving items to the right until you find the correct spot to insert aircraft Z, correct? Yeah. So in this case, I will move Y and X to the right by one, and then aircraft Z will be added to the front. Right? Yes? Okay? So that's enqueue. How about dequeue? Dequeue in this particular implementation is easy. You just return the frontmost item because that's the one of the highest priority. Okay? Then you just advance your front pointer. Okay? So this enqueue will take what time? O(n) time, right? Because possibly you need to shift every item in your queue to the right by one and then insert the new item at the front. Right? Dequeue is simple. It's just a one time. I just return the one at the front and advance my front pointer. Right? Yeah. So this is one way to implement a priority queue with knowledge that you already know. Yeah. Okay, next. There's another way of doing it, yet again using a circular array-based implementation. Okay, and now the property that needs to be maintained is slightly different. Okay, the property is just this: dequeue operation always returns the correct item. Okay, so I don't care how they are inserted. Okay, I just care that when you dequeue, you return me the item with the highest priority. Okay, that's the property that must be maintained. Okay. So enqueue for this particular implementation or strategy is easy. Okay, you just take the new item, insert it at the back, right? So advance your back pointer, insert it at the back. Yeah. So in this case, aircraft Z comes in, insert at the back. Yeah. How about dequeue? Dequeue, since it's not sorted, right? correct? The highest priority, the item of the highest priority might not be at the front of the queue. So now I need to scan through my entire queue, right? Start from the front pointer, go all the way to the back pointer. Okay, find the one that is the highest priority, right? And then remove it from the queue, right? So in this case, I need to scan all the way to the back. Oh, I found it. Aircraft Z is the one with the highest priority. So remove it from the queue. Okay? So in this case, since it's just at the back, I remove it, I just decrement my back pointer, that's it. Okay? But if it's, like for example, somewhere in the middle, what happens? If you remove it, there's a gap, correct? So you need to close the gap, because in this implementation, everything should be in contiguous memory. Yeah? So you want to close the gap. So how do you close the gap? So everything to the right of the item you dequeue, right, needs to be shifted one to the left. So this takes what time? O(n) time, right? Right. So in this particular implementation, enqueue is fast, just O(1) time, just add it to the back. But then dequeue is slower. It takes O(n) time. Yeah? Yep. Yeah, let's get. So close it. Okay. So if we just stop at 1020 knowledge, okay, this is what you have, okay? These two circular array-based strategies. For the first one, enqueue takes O(n) time, dequeue takes O(1) time. For the second one, enqueue takes O(1) time, but dequeue takes O(n) time. Okay, so which one do you think is better? Which one do you think is better? The first one or the second one? Depends. Depends. Okay, I would argue that actually, okay, just based on the knowledge you know, okay, the second one is actually better than the first one. Okay, depending, of course, depending on the application. Why do I say that? Well, if your application has lots, oh no, first one, yes, second one is better than the first one. If your application has lots of enqueue, but then very few dequeues, then the second one is better, right? Correct? Because enqueue is just O(1) time, right? And then dequeue is O(n) time. Okay? But then there are very few applications where I can say that I have lots of dequeues but very few enqueues. Why? Because you can only dequeue as much as you enqueue, right? Correct or not? Yeah, so if I want to say, my opinion is that second one is slightly better, okay? But both of them have a weakness, right? One enqueue is slow, one dequeue is slow. Of course, if your input size is not very big, O(n) time, linear time, O(n) is linear time, right? Linear time is actually quite fast already. Okay, but what if, let's say, you have billions and billions of items? So O(n) is actually slow in that sense. Okay, so can we do better? Can we do better? Yeah, of course you can do better. If you cannot do better, then this lecture finished already. Right? You already, this one is the best that you know of. I can go home. Okay? So of course you can do better. Okay, so how to do better? Now we will introduce a new data structure for you to learn, okay, which is the binary heap, which we will use to implement this priority queue abstract data structure. Okay. Okay. So what is a binary heap? Okay, binary heap is basically a complete binary tree. Okay, the structure is a complete binary tree. Okay, but before that, let's do some revision for those of you who have taken 1, 2, 3, 1. Okay, those who have not taken 1, 2, 3, 1, then this is a new concept. What is a tree? Okay, so what is a tree? Those who have taken 1, 2, 3, 1, what is a tree? It's a non-linear data structure, right? It's a non-linear structure, correct? It's non-linear structure, okay, where items in the tree are organized in nodes, correct? Nodes like your linked list, like that, yeah? And how are they related? They are related in a hierarchical fashion, right? In a hierarchical fashion. So at the top of your tree is the node called the root, yeah? And then at the bottom of your tree are nodes called leaves. You know, every other node or vertices, as they call it in your tree, are internal vertices. They are called internal vertices. Okay. If you look at some mathematical text, right, sometimes they will include the root as an internal vertex also. Okay, but for our course, we treat it separately. Okay, so just remember this slight difference in definition. Okay, so there is root, They are the leaves, and then they are the internal vertices. Okay? So, in general, okay, internal vertices, if I look at internal vertex, right, okay, it has a relationship with other kinds of vertices, okay, in your tree. For example, let me look at this one. This is internal vertex, right? So this internal vertex is related to one vertex called its parent, okay? So in this case, it's the one that is just above it, okay, in the tree. So the root here is called the parent, right? The parent of this internal vertex. And then just below it, it has what you call children, right? So these two nodes are called the children of this internal vertex. Yeah. And for the root has no parent because it is at the top. And then for leaves, since they're at the bottom, they have no children. Okay, that's it. Okay, so this is a tree, basically a tree structure. It represents a non-linear kind of relationship because if you look at this tree, can you organize everything into a linear sequence? You can't, right? Correct? Yeah. So this is a non-linear structure. Okay. So this is a tree. Next, what is a binary tree? What's a binary tree? It's a tree where each vertex has at most two children, right? Okay, so you can call it the left child and the right child, right? Yeah. Okay, and what's a complete binary tree? So now you know what's a tree, you know what's a binary tree, what's a complete binary tree? Okay, complete binary tree is simply a binary tree where every level, okay, except possibly the last level, is completely filled. Okay, and all nodes are as far left as possible. Okay, that's the definition of a complete binary tree. Okay, so if you look at this example here, is this a complete binary tree? This is right. If you look at it, what level? Okay, this is the first level, second level, third level, fourth level, which is the last level, correct? So you see that every level is filled, except here, the last level is not completely filled. But all the vertices or the nodes are as far left as possible. Okay, so this is a complete binary tree. Okay, now what if the last level is filled also? It's called a perfect binary tree. Okay, it's called perfect binary tree. Okay, so it's still a complete binary tree, but it's a special kind of complete binary tree called perfect binary tree. Okay. Okay, important question. If you have a complete binary tree of n items, what would be the height of this complete binary tree? Okay, what do I mean by height? Let me define it. Okay, height is equals to the number of edges from the root to the deepest leaf, to a deepest leaf. Okay, if you think about it, if you look at it, right, so this is the root. Okay, in this example, this is the root, this is the leaf. So it's the number of edges, right? So in this example, I have 1, 2, 3, 3 edges. So it's equivalent to the number of levels minus 1. Right? So in general, if I have n items, then what is the height of my complete binary tree? Okay. So I'll give you 4 options. O(n), O squared n, O log n, okay, O1, and the rest of the people don't know. Okay lah, it's number 3 lah, okay? Number 3. O log n, okay? O log n. So memorize this, okay? Because we'll need it for almost all of your time analysis, okay? Or binary operations. Okay. Okay, so what I described to you is an abstract structure, right? The binary heap is basically a tree, a complete binary tree. Okay, but we need somewhere to store this complete binary tree in our program, yeah? Right, so we need a concrete data structure to do this. Okay, so there are actually many ways of representing or storing a complete binary tree, okay? One way is to actually create nodes and then have references, okay, in a way that's similar to how you create linked lists. Okay, so that way of creating a tree structure, we will deal with it next lecture. Okay, in this lecture, we will use a different way of storing a complete binary tree, okay, which is using a one-base compact array. Okay, what is called one-base compact array? One base means that I store items in the complete binary tree or my binary heap, okay, starting from index 1 of my array. Okay, and it is compact in the sense that all the items are stored continuously. There are no gaps. Okay, so given this particular complete binary tree here at the bottom of the slide, okay, this is how it would be stored, okay, in an array, a one-base compact array. Okay, so at the top, okay, which is the root, you will store the value of the root at index 1. Okay, start from index 1 instead of index 0. Okay, then you will go down the levels, okay, go from left to right, okay, and then store them sequentially following the root. Okay, so I have 90 at index 1, then I go to the next level, right? I have 19 at index 2, 36 at index 3, go down to the next level, 17 at index 4, 3 at index 5, 25 at index 6, 1 at index 7, and then go on to the last level, 2 at index 8, 7 at index 9. Okay, so the last index also represents the size of your binary heap. Okay, so usually we will have a variable or pointer called binary heap size or heap size that indicates the size of my heap, of course, and also where is the index of my last leaf, okay, of my binary heap or complete binary tree. Okay, so of course you must make sure that your heap size is smaller than the size of your array, okay? Otherwise, if it exceeds it, you need to expand your array. Yeah. Okay. Now, given this way of representing or storing your complete binary tree, okay, we must have some way to navigate through the tree, right? We must have some way to get from one vertex or one node to another node. Okay, for example, if I am at vertex 2 here, okay, which represents the node containing 19, okay, I must have some way to go to my parent, and I must have some way to go to both my children, right? So these are called the navigation operations that I need. Okay, so from here, can you tell me how you would go from a given node, okay, given its index, okay, to its parent? How do you get from a node to its parent? Divide by 2, correct? If you look at it, yeah, looks to be the case. Okay, 2 divided by 2 gives me 1, which is my parent, right? Then 3, 3 divided by 2 gives me 1 point something. Eh? Okay, so I need to take the floor, right? Yeah, just my current index, the current index divided by 2 floor. Or do integer division, right? Integer division. Okay, so that's how you get from current index to parent index. Okay. How do I get from the current node or current index to my left child? So my index times 2, right? Correct? Yeah. 2 times 2 gives me 4, correct? 3 times 2 gives me 6. 4 times 2 gives me 8. Okay, so that just times 2. Right child? Times 2 plus 1, correct? Yeah. Okay. So very simple navigation operations. Okay. So parent of I, okay, will be floor of I divided by 2, or basically just integer division, okay, I divided by 2. Okay, except when I is 1, when you have the root. Root doesn't have any parent, okay. And left of I will be 2 times I, and you have no left child when left of I is bigger than the heap size, which is correct, right? For example, here I am at index 5. What is the index of your left child? It will be 5 times 2, 10, right? But then that exceeds the heap size. So actually you have no left child, okay. And same thing with the right child. Okay, right of I is 2 times I plus 1, except when right of I is bigger than heap size. Okay. Okay, another question. Why don't we start storing from index 0 instead of storing from index 1? So why not 0 base instead of 1 base? Now look at it from how we navigate. Look at it from how we navigate. if we are index 0, right? Then what is left child? 2 times 0, which is 0. So you're actually not going to your left child, right? Correct? So we start from 1 instead, start from 0. Yes. Yes, you can. If you are going to start from 0, right, you need to change all these formulas, right? You need to change it. Okay, next, later on in the lecture, I will show you the implementation of this one, and then we'll see why actually we use this particular formula. Okay, because there's very efficient implementation for it. Okay, so we don't mind just sacrificing one space lah. Okay, index 0. Okay, it doesn't really hurt us. Okay, but in return we gain very quick navigation operations. Okay, sure you can. So if you start from 0, I just need to change all these formulas for the navigation operations. Okay. Okay, so other than binary heap being a complete binary tree, okay, that is the structure, okay, the structural property of a binary heap, right? It also needs the property that every data structure must have, which is properties on the items that is stored inside my binary heap. Okay, so we call this the binary heap property. Okay, binary heap property. So for a max heap, the binary heap property is like this. Okay, the value of your parent, of the parent of any node, must be bigger than the value of the node. Okay, that's a max heap property. Okay, if it's a mean heap, then the mean heap property is this. The value of the parent of any node must be smaller or equals to the value of that node. Okay, so max heap property, mean heap property. Okay, so for this particular lecture, we will just be dealing with max heaps lah. Okay, max heaps. Okay, and we also ensure that all the numbers are distinct. Okay, so in this example given here, obviously this is a structurally a binary heap because it's a complete binary tree, but does it fulfill the max heap or mean heap property? Just eyeball this particular tree. Does it fulfill one of these properties? What is this heap? It fulfills the max heap property, right? Correct? Yeah, you look at every node, okay, except the root. Okay, 19 is smaller than 90, right? And 17 is smaller than 19, 3 is smaller than 19, 7 is smaller than 17, 2 is smaller than 17, 25 is smaller than 36, 1 is smaller than 36. It fulfills the max heap property. So this is a max heap. Okay, this is a max heap. Okay? Of course, can we write the max heap property like this, for example? The value of a particular node at I must be bigger or equals to its left child and also bigger or equals to its right child. Is this a valid way of defining max heap? No? Is it valid? It is valid. Okay, it is still valid. It is a valid way, but of course, one thing is that this is longer lah. Okay, this way we define it is a shorter way, and you have to be careful because for a given node, it might not have a left child or a right child. Okay, for example, yeah, 3 here, it's a leaf already, right? It does not have a left or right child. Okay, then if you are in your program, you are trying to program and check whether something is the structure given to you is actually a binary max heap, right? Then if you do A left I, A right I, you will get a what? Array index out by exception. So you need to be careful. Okay? Okay? But in general, this is also valid way of defining max heap property. Okay? Okay, so another quick question. Largest element in a binary max heap is stored where? The leaves. One of the internal vertices. Anywhere in the heap. Oh, the root. Yeah, okay, the root. Okay, max heap. About mean heap. Smallest element where? Mean heap. Also at the root, right? Yeah. So it's a quite intuitive data structure, right? Yeah. Okay, so now we will go to, okay, maybe I'll show you. So we'll go to Visual Algo. Where is it? Okay, So basically, this you click on binary heap on VisualAlgo, it will start the e-lecture mode. You can just escape and then go to exploration mode. So here I've already created a heap. Okay, so what heap is this? I've created a max heap, right? Yeah, it's a max heap. So this is a max heap. Okay, so let's look at, someone just subscribe. Okay, let me just go back to the slides. Okay, so there are a few operations that a max heap, the heap has. Okay, just come back here. Okay, just click on this left side. Okay, you'll see some of the operations that you have. Of course, you have some way to create the heap. Okay, then you have two major operations on the heap. One is to insert a new item into the heap. Okay, insert V. So just insert it using the key value or its priority value. Okay, next is to extract max. Okay, extract the maximum item out of this max heap. Okay, and after you can perform heap sort. So I will talk about these one by one. Okay, let's come back. Okay, let's look at the first operation, which is to insert an item into your heap or into your max heap. Okay, so this is the pseudocode for doing insertion. Okay, so insert an item V. First of all, I have a heap size, right? I have a variable heap size, that keeps track of the size of the heap. So I just increment it. Okay, then I set a heap size, okay, at index heap size to be the new item. So I just add it right at the back of my heap. Okay, but if I do that, right, I might have violated max heap property, right? So I need to fix it. Okay, I need to fix it. Or so-called heapify my heap again. So I use this operation called a shift up operation. Okay, just pass in the heap size, which is the index of where the new item is. Okay, is stored. Okay, let's look at how you do shift up. Okay, so shift up, as the name suggests, is basically this. Because the new item is added as the last item in your heap, right? It is added as what? It must be added as a leaf, right? Right, how are you adding it? Imagine I already have a binary heap. If I'm adding it as a new, okay, if let's say the last level is not filled out, right? I'm actually adding it to the right. Correct? So I'm adding it to the right. You can imagine that, right? Alright, never mind, we'll demo it later on. Okay, then from that point onwards, because it might not be in the correct place, okay, I might be violating binary heap property or max heap property, I need to shift it up, okay, until it is in the correct place. Okay, so this is what this shift up operation is doing. So this name is not unique. You can have lots of other names like shift up, bubble up, increase key. Okay, so what are you actually doing here? What you're doing is basically this. Okay, there's a loop, okay, and then it will keep looping while you find that the current node is not the root, and also the parent of the current node is smaller than the current node. Okay, that means that max heap property is violated. Okay, then what do? You just swap the two values of the node, its parent node. Okay, update index to be the parent index, and then continue doing this. Okay, can? So this is shift up. Okay, let's demo this on VisualAlgo. So I have this by max heap already. Let's just add a new value. Let's say, what should I add? Let's say I add 7. Okay, add 7. So where would 7 be added? So there are 1, 2, 3, 4, 5, 6, 6 nodes or 6 items currently inside your max heap. So where is the new item added? It's added at index 7, right, which is just added to the right of the last level. Yeah, the new item added to the right. Okay, sometimes the values don't come out. So what you have to do is basically resize it. Okay, this is a known problem of VisualAlgo. Okay, if you find that something is not drawing very correct, resize it. This will force a redraw. Okay, this will force a redraw. Okay, so you see it. Okay, so 7 is added at index 7. Okay, and then if you look at it, is max heap property violated? No, right? So how do you know? Well, if you call shift up will basically just check 7 here with its parent 19, right? So it is smaller than its parent, so it must be in the correct place. Yeah? So we are done. Boom. N. Yeah? Okay, this one is simple. Okay, let's add a new one. Let's add 24. Okay, so 24 will be added where? So this, currently all my levels are filled already, right? So actually 24 will be added as the new node of the new level. Okay, leftmost. Okay, oops, don't do first. Okay, add 24 at index 8. Okay, which is the start of the new level. Okay, so it's basically a child of index 4, which is correct, right? So 8 divided by 2 is 4, so it's added here. Yeah. So at this point, is maxi property violated? Is it violated? It is, correct. Yeah. 24 is actually bigger than 1. So what do? Swap them. Yeah. So swap. Okay. So now 24 is at index 4. Yeah. Is maxi property still violated? It is, right. 24 is bigger than 3, its parent. Okay, swap. Okay. Then at this point, is maxi property violated? Yeah. No. 24 is smaller than 25, right? So it is in the correct position. Okay. So you have fixed the maxi property or heap, re-heapify your heap. Okay. Okay. Next, let's try adding 90. Yeah, of course, 90 will be added as the new last leaf. Okay, here. Okay, so what happens now? 90 will solve with 3, right? Correct? Then 90 will solve with 24, right? Then 90 will solve with 25, right? So at this point, this is the second condition when you stop. Because I hit the root already, I've hit index 1. Okay, which also means that I'm the biggest value, okay, in the max heap. So I stop. And you find that, yeah, this entire heap is fixed. Okay? So this is insertion. Okay? Now, why does this way of doing insertion actually works to re-heapify your entire heap? Okay. Let me just give you the intuition. Let me just come back. Okay, let me just add it here. Okay. At the point where you add it, okay, at the point where you add it, you will find that it must be added as a leaf, correct? Any new item added or any new value added into your max heap must be added as a leaf, correct? Yes. Now at this point, you will find that this particular subtree, okay, the subtree that includes the new node and its parent, okay, anchored by its parent, right, is the one that could violate maxi property, correct? Yes. Now, if it is violated, what I do? I just swap, right? I just swap. Okay. Come back here. So after I swap, you'll find that for this subtree, it is fixed already, correct? It is fixed. Yeah. And then everywhere else, if I look at everything else, right, maxi property is not violated because I didn't touch any of them, correct? Yes? But if I look at this one, now, that means that this one 90, 90 is at index 4, right? Now I look at the subtree anchored by its parent, 24. This one is subtree, right? It might be violated again, right? Yes? But now, if I swap, boom, then this entire subtree must be fixed already, right? Must be a heap, right? Yes? And again, at this point, this entire subtree and the rest are fixed. But now if I look at the bigger subtree here, then entire thing, that means that compare 90 with its parent, 25, right? It might still be violated, right? The maxi might still be violated, right? Property. Okay, so what do? Swap them again. When you swap them, this entire subtree must be fixed already. And since this is basically the entire tree, right? So your entire tree is fixed. Okay? Okay, so this is sort of the intuition why shift up will work. Okay? go back to the slides. Okay, analysis. What is the time complexity of shift up? I always start from a leaf, right? And then I start shifting up. So if let's say I consider a comparison and a swap to be one shift operation. Okay, so that's one shift operation is a basic operation, right? So how many shifts do you need at most? How many shifts do you need at most? Log n, right? Correct, because why? I'm shifting all the way from the leaf to the root. Correct? And you remember what's the height of complete binary tree? O log n, right? Yeah. So time is this. O log n. Yeah. But is this very accurate? Sometimes I don't need to shift, right? I find that, hey, I am at the correct position already, done, boom. Or I just shift it to the correct level where I'm at, and then I'm done. Right? So this one will not always happen, right? I will not always shift all the way to the root. Okay? So more precisely, it is actually OH, where H represents the level where you should be at. Correct? Yeah? Yes? Okay. So since shift up is in time OH, then what is insert? What is the runtime of insert? Well, insert here, these two statements are one time, right? So actually it depends on shift up. So insert is also OH time. Or in the worst case, it's O log n time. Yeah. Okay, let's go to the next operation, which is extract max. That means you remove the maximum element from your binary heap. Okay, so where is the maximum element in the max heap? It's always at the root, right? Right? Yes, but if you remove it, that means that if you imagine if I remove it and don't do anything else, my binary tree becomes disconnected, right? Yeah, so what do? What you do is this. First, you save the value, okay, index 1, which is the root, into a variable max v. Okay, then you take the last leaf, that means the value at heap size. Okay, replace the root. Okay, so now I take the last leaf, replace the root. Okay, now of course I decrease my heap size lah. Okay, because I already removed the root. And then what do? You'll find that if I replace the root with the last leaf, right, my max property could be violated also, right? So now what can I do? I should shift down, right? I should shift the value down into its correct place. Okay, so you do a shift down operation. Okay, so how do you do the shift down? Okay, that's how you do it. Okay, in shift down, what you do is this. You take the current node, okay, starting from the root, then you find the largest value between the current node and its two children. Okay, find the largest value. Okay, if the largest value is not the node itself, okay, then just swap with its larger child, because the largest value must be one of its larger child, right? Okay, it must be its larger child. So swap with it. Okay, swap and then continue this operation. Okay, until the current node is the largest value, okay, among itself and then its two children. Or it hits the leaf, and that's it. Okay? So basically, this is how it's done. Okay, first, you set the current node to be the maximum value. Okay, of course, set its index to be the maximum value index. And then you check against its left child, if I have a left child. Okay, and the left child is bigger than max value. Okay, update max value, update the index to be that of the left child. And then check with the right child. If I have a right child, right? So this, and then the right child is bigger than the max value. Okay, update max value, update max ID. Okay, then I will check. If max ID is not equal to I, that means that the largest value is not myself, it's one of my children, swap with them. Okay, update I, and then continue this operation of shifting down. Otherwise, I'm in the correct position, break up. Okay, or you will just continue doing this when I is smaller than the heap size, small equals to heap size. When it's bigger than heap size means I hit the leaf level. Okay, stop. Okay, So let's demo this on VGL Go. Let's remove these. Okay. So if I call extract max once, okay, what happens? I will remove 90, right? Like I said, if you remove 90, then you don't do anything else, you are basically disconnecting your binary heap. So I will take the last leaf, which is which one? It's all right. The next 9, okay, or value 3. Then replace, put it at the root. Okay? And now at this point, I will just call my shift down operation. Okay? Shift down, so 3 will compare with 25, compare with 19. Right? Which one is the biggest one? 25, right? So you will swap with 25. Okay? Now at this point, 3 will compare with 24 and 2, right? Which one is the bigger one? 24, right? Swap. Okay? Then at this point, 3, I will compare with 1 only. Oh, I am bigger than my only child. Okay, so I'm at the correct place. And then you see that I have reheapified my heap. Okay? Let's try again. Extract max. So 25. Now I replace the root with 1, right? And then now 1 compared to 24, 19. Swap with 24, right? 1 compared with 3 and 2, swap with 3, right? And then at this point, you find that, oh, 1 has hit the leaf level. Okay, so you will stop. Okay, and I have already heapified everything. Okay? So, same thing, why does shift down work? Okay, to reheapify your entire heap. Okay, let me just go back. Okay, after I remove 25, right, I replace 25 with 1. Okay, so at this point, if you look at it, only 1 here is out of place, right? Only 1 is out of place. Okay, for this entire tree. Okay, so when you perform one swap, okay, you'll find that at this point, 1 is out of place for this subtree where it anchors, right? That everything else is okay, right? Then when you do another swap, you'll find that now 1 here might be the only one out of place for the tree it anchors. But at this point, 1 is the only node of the tree, right? So it's actually in the correct place. Everything else is fixed. Okay, so the entire tree is actually fixed now. Okay, so that's the idea. Okay, with shift down. Okay, so let me go back to the slide. Okay, again, what is the runtime for shift down? What is runtime for this shift down operation? In the worst case, I always start from the root, okay, in this case. But in the worst case, I will shift all the way down to a leaf level, so it's O log n, right? But just like the analysis for shift up, actually the more general, the more correct one is that you will shift to the level you need to be at, right? So it's still OH time, right? OH time. Okay, so basically extract max, in the worst case is O log n, more generally is OH time. Okay? Okay, so basically you know how to insert an item, you know how to extract an item. So if I am using a binary heap, okay, to implement my priority queue, then it's very simple, right? And Q is just insert. Call the insert operation of a binary heap. Okay, DQ is just extract max. Okay, yeah. So using a binary heap, now I have this. Okay, binary heap, insert key, in the worst case log n time, right? Okay, for NQ, and then DQ, which is extract max, worst case also log n time. Okay, so I'm slightly slower than O1 time. Okay, based on my circular array implementation. Okay, but both of these operations are faster than the worst case for my circular array implementation, which is O(n) time. Okay, so this binary heap is a good middle ground. Okay, it's a good middle ground. Okay. Okay, so why don't we take a short break, 5 minutes break, and then we will come back. Okay, to talk about other stuff we can do with the binary heap. Okay. Okay, let's continue. Okay, let's continue. Okay, so a review question. You have seen merge sort in 1020. Okay, you can sort n items in what time? Review of merge sort. O n squared. O n log n. O n. O log n. O log n. O log n. O n log n. More people should raise their hands. O n log n. It's O n log n, right? Correct. Yes. So for comparison-based sorting, the best that you can do is O n log n. Okay, O n log n. So merge sort is O n log n. Yeah. Okay, next we will see another sort, which is heap sort. Okay, later on. Okay. Now let's look at another operation. Obviously, if you want to create a heap, you can insert it one by one, right? You can insert the items one by one. Okay, then of course, you have what we call a slow way of or naive way of creating the heap from an array of input. Okay, so this is the naive way. Okay, just take your array of input, get its size, right, and then set the first index of your binary heap to 0. Yeah, because we don't care about that one. Yeah, set to 0. And then you go through your array, so you have a for loop that goes through the array from index 0 to n minus 1. For each item in your array, just call the insert operation, okay, to insert into your binary heap. Okay, so what is the time for this way of creating a binary heap from a list of n inputs? Okay, basically it is is dominated by this for loop, right? Correct? So the for loop runs n times, n inputs. Each time you call insert, at worst it's O log n time, right? So it's O n log n, right? So creating heap in this way will be O n log n time. So is there a faster way of creating the heap? Okay, obviously there is. Okay, so this is a faster way. It's O n version. Okay, it's O n version. Okay, so how do we do this O n version? Okay, you take in the array of inputs. Okay, same thing, get the size. Okay, set the first index of your binary heap to be 0. And then you just go through, okay, this first for loop. You're just going through the array of inputs and copying it to your binary heap. Okay, you're not calling insert operation, you're just copying it over. Because both are actually arrays, right? Just copy over. Okay, so the one at index 0 in your input, right, will be copied to index 1. And at index 1 copied to index 2 and so on and so forth. You just copy over. So this will be done in O n time. Correct? Then I have another for loop. Okay, that starts from the parent of the last leaf, which is the index n. Start from the parent of the last leaf. And then go backwards to the root. And then for each of these indices, call shift down. If you think about it, well, if I start from parent of the last leaf, go back to root, there is big O of n divided by 2 number of nodes, right? Correct? So this for loop will go big O of n divided by 2. Okay, run this many iterations. And then I call shift down on each of these indices or each of these nodes, which in the worst case is log n, right? So, reasonably, it should actually still be O n log n, right? It actually is not O n log n. Okay, we will show you why it is not O n log n. It's actually O n. But before that, let me demo how you actually do this. Okay, fast create heap. Okay, let me just do this. Let me 25. What did I add just now? Add 7. 190. Okay. So given this list of inputs, okay, so let me use this fast create heap method. Okay. At the beginning, I will just copy everything into my binary heap. Yeah. So this is what I have. Okay, 19, 3, 17, 1, 2, 25, 7, 24, 90. Yeah. And after I copy it, I will start from the parent of the last leaf, which is the last leaf here. 90, right? So the parent will be 1, correct? So I will call shift down, okay, from this node, and then every node going backwards towards 1. So I will call shift down index 4, shift down index 3, shift down index 2, shift down index 1. Okay, so you see what happens? Here I call shift down on index 1, index 4, which is the value 1. Then what I do? I will swap with the largest child, right? Which is 90. So swap. Boom. Okay, so this is done. I go to index 3, which is 17. Same thing. I find the largest value among myself and my 2 children, swap with the largest value. So swap with 25. Yeah, boom, done. Then come to index 2, right? Which is 3, blue shift down. So I swap with 90, correct? Then at this point, I swap with 24. Okay? Now I come to, so this one is finished already. Now I come to index 1. Right? Index 1, do shift down. So shift down 19 will swap with 90, right? And at this point, 19 will swap with 24, right? Then at this point, 19 is the correct place. Done. I have gone all the way back from index 4 to index 1. Call shift down on each of those indices. And if you look at it, I have reheapified my heap. Right? Yes? It is not a valid max heap. Correct? Yeah. So, why does this work? Okay, number one, before I do analysis of why it is ON time, why does it work? Okay, let me just go back. Oops. And go back all the way to the front. Okay. Now, where do I start calling the shift down? From the parent of the last leaf, correct? So I start from this, right? And then I go backwards, right? Now, you remember, in shift down, right? The assumption is that the value you are looking at is the only one that's out of place, correct? So in this case, I start from the last parent of the last leaf, which is, if you think about it, is actually the last internal vertex. Think about it. It must be the last internal vertex, correct? Because after this, if you go to the right, it will be all the leaves already, right? It will be all the leaves already. It's actually the last internal vertex, which means that what? Both its children must be a leaf, right? Both its children must be a leaf, right? So since both children are a leaf, basically you can view this as the smallest subtree you can have, right? Other than having one single node. So if I do shift down, from here, we will find that this entire subtree must be fixed already, right? Right, then I move to the next index, okay, index 3. Okay, move to index 3, right? So in this case, index 3, well, has got 2 leaves, correct? And then basically it will be the same case, right? Yeah? So it will swap. And then this one will be fixed already, right? And then I'll come to index 2. Okay, at this point, index 2 has 1 leaf and then 1 child which is not a leaf. But if you think about it, that child I must have already called shift down on it, correct? Because I'm going backwards. So, which means this, right? At any vertex, either my child is a leaf or it must be some internal vertex which I have already called shift down on. Yeah? So, this means that everything except for the node that I'm looking at, right, is fixed already. Right? So if I call shift down on that node, the entire subtree that's anchored by that node must be fixed. Right? So at this point, I call shift down on 3, boom, boom. Okay? Now after I finish that, right, then this entire subtree is now fixed. Right? And then I come back to index 1. Right? Index 1, same thing. My left child is index 2, index 3, which I already called shift down on. So these 2 subtrees are already fixed. So this is the only one that's out of place. So this is like your standard extract max, right? Extract max, then call shift down. Yeah. So after call shift down on this entire tree is now fixed. Okay. Okay. So that's the intuition behind why it works. Okay? Okay, now, how come this is not n log n? How come this is just On? Okay, let's do the analysis of this one. Okay, so this is the inventor for this fast heap create method, okay, which is Robert Floyd. You will see him again later on, okay, because we will use another algorithm of his, okay, later on in the course. Okay, so before we do the analysis, I need a bit of setup. Okay, what is the height of a complete binary tree or binary heap of size n? Just now we said it's big O of log n, right? Right? Can we give a more precise formula for it? Yeah, sorry? Log 2n, okay, log n lah, okay? So all our log is basically base 2, yeah. So log n? Exactly. Just this. It's just log n floor. Okay, you can try it, you'll find that this is correct. Okay, log n floor is correct. Okay, so if, okay, this is the height of a complete binary tree. What if it is the height of a perfect binary tree? Of course, this one will still work lah, right? Whether it's, because perfect binary tree is just a more specific case of a complete binary tree. So if it's a perfect binary tree, is there another way of representing the height? It's perfect, huh? Every level is filled, including the last level. It's perfect. It looks like a perfect triangle. Another way? Okay, so for perfect binary tree, this one will be equals to log n plus 1 minus 1. Yes, correct. Yeah? So you can try it. At the bottom here, I have actually a perfect binary tree, right? With 15 elements, 15 items. So 15 plus 1 gives you 16, log of 16, log base 2 of 16 gives you 4, right? 4 minus 1 gives you 3. So that's the height, which is correct, right? There are 3 edges from the root to any leaf here. Okay? So this formula is correct. Okay, next. What is the cost to run shift down? I. For any I. Well, just now we said in the worst case it's O log n, right? Which is correct. But more generally, it should be what? Big O of h, right? It depends on which level you're at. Okay, imagine that I label the levels like this. At the root is the highest level, right? Correct? Highest level will be level what? Log of n floor, right? Correct. So in this case, basically it's 3. Okay? Then the next level will be 2, next level will be 1, and the leaf is at level 0. Okay? So what is the cost of running shift down on I? Depends on which level is at, correct? Okay? From there, it shifts all the way down to the leaf level. Right? So just call this, the cost will be, h. Okay? H. Yeah. Okay. How many nodes are there at level h of a perfect binary tree? How many nodes are there? Anyone? Is it 2 to the power of log n minus h. Is this correct? 2 to the power of log n floor minus h. Correct, right? Let's try. At level 3, which is my root. Okay, how many nodes are there? One node, right? Log of n floor gives you what? In this case, 15. Floor gives you 3, right? 3 minus height. Where's the height of 1? Where's the height of the root? 3, right? So it's 2 to the power of 0 gives you 1. Correct? Yeah? At level 2, it's basically 2 to the power of 3 minus 2, right? So I have 2. At level 1, 2 to the power of 3 minus 1 gives you 4, and so on and so forth. So this is correct. Okay? So this formula is correct. Any other way? Any other way? Any other formula? There's another one. Okay? Is this or is this correct? Wait, let me see. And it's 15, 15, divided by 2, 15, ceiling 3 plus 1, 16. Yeah, I think this is correct. Is this correct? Try to plug it in. Okay, this one is n. Okay, this one is not h. Let me use capital. Okay, it's capital. Okay, so ceiling of n divided by 2 to the power of h plus 1. Is this correct? At level 3, so 2 to the power of 3 plus 1, 2 to the power of 4, 16, right? 15 divided by 16, ceiling is 1. Correct? At level 2, 2 to the power of 2 plus 1, 2 to the power of 3 is 8. 15 divided by 8 is 1 point something, right? Ceiling gives you 2. It's still correct. Level 1 is 2 to the power of 1 plus 1, 2 to the power of, which is 2 to the power of 2, 4. 15 divided by 4, 3 point something. Ceiling, correct, is 4. Okay? Last level, 2 to the power of 0 plus 1. So 15 divided by 2 gives you 7 point something. Ceiling, 8. Correct. Yeah. So this is another way of representing it. Okay? Now, in the worst case, okay, when you do perform the fast heap creation, right, at each level, the vertex must be shifted all the way down to the leaf, correct? Yes? Correct? So that will take what time? H time, correct? Depends on which level they're at. Yeah? Now I have this many number of nodes at a particular level. So what is the total number of shift operations you have for any particular level? This one times H, right? Correct? For any particular level. Yeah? Then total number of shift down operations for your entire create heap, sum for the all possible levels, correct? Sum it for all possible levels, right? Yes? Okay, let me just, oops, wait. Okay, let me remove everything here. Erase all the ink. Let me use a white screen. Okay, so I said for a particular level, okay, let me ignore the floor and stuff like that. It doesn't change our analysis. Okay, so log 2n minus h times h, okay? Total shift operations. At a level h, correct? Yes? Because 2 to the power of log n minus h is the number of nodes you have at a particular level. Okay, h is the total number of shift operations you need to perform for each node at that level. Right? And you have this sum for all the levels, 0 to log n. Okay, 2 to the power of log n minus h. Minus h, this is total shift operations. Correct? Yeah? So, basically I can say that my fast heat create is big O of this lah. Log n to the power of log n. 2 to the power of log n minus h is basically 2 to the power of log n divided by 2 to the power of h, right? Right? Times h. Yes. Now can we simplify this? What is 2 to the power of log n? Is your logarithmic identities. This must be equals to n. Yes, correct. Then I can factor this n out, right? Yeah, so it becomes big O of n summation h equals to 0. My thing saying it already. Okay, sorry. So this is h over 2 to the power of h. Okay? Right? Let me make it a bit straighter. So this is equals to, can we simplify it further? Can we simplify it further? I mean, usually when we want to do these kind of things, we want to have a very simple term, right, for a big O, right? So this is not simple enough for us. So we need to simplify further. Okay, so this one, we can take it to be actually, instead of summation from h0 to log n, I sum it to infinity. Yeah, so big O of this is actually big O of this. Okay, oops, wait. No. It's not here. Oops. Let me come back here. Where's my eraser? Okay. So summation. Oh, why did I keep writing summation? Sorry. My n. Okay, my n. Okay, this summation h0, and this one is infinity. Okay, h over 2 to the power of h. Okay, now is this any better? Doesn't look much better, but actually it's better because why? This thing, okay, is the differentiation of an infinite geometric series. Does that? So all of you will be, so what? Okay, so it means this. Okay, it has the general form like this. Okay, h to infinity, h x power h. Okay, which, lucky for us, has a closed form, which is x over 1 minus x squared. Okay, so what is x in this case? If you look at it, what's x in this case? X is actually half, correct? It's half, right? If you plug in half here, you exactly get this thing. Yeah? Okay, so let's plug this in. So this one here, let me come here. So here, big O of, let me just, okay, take out the n. And here, then I have half over half squared, right? Which gives me what? Half divided by half squared is half over 1/4, which gives me 2. So this is 2n, which is big O of n. Okay? So through some obscure mathematical manipulation, I get big O of n. Okay? Can? Okay, so let me go back. Ding, oh, yeah, it disappeared. Okay, so what I just described is basically what is stated here lah. Okay, except here you are using a different way of calculating number of nodes for level H. Okay, so if you are not very convinced, right, you just take this particular summation. Okay, you work out a few terms. You work out a few terms. Okay, then after that, what do? You plug it into Wolfram alpha. And then it will tell you what is the summation of this thing to infinity. Then you come up with the value 2. Okay? So it's actually big O of n. Yeah. Okay? So, done. So fast heap create On. Okay? Instead of the more sort of intuitive On log n. Okay? So now we can actually do heap sort. Okay? Do heap sort. Heap sort is like this. In heap sort, you take in the array of inputs, and then you use your fast build heap operation, which is what? This is actually big O of n, right? Okay. Then after that, you just get the size, okay, of your heap, and then you have a for loop. You just keep calling extract max. Okay. For each call of extract max, I just get the value, put it back into my array. Okay, in reverse order. So now I have everything that's sorted from smallest to largest, right? So it's in ascending order. Okay, that's how you do heap sort. Just keep calling extract max. So the first one extracted the biggest one. Second one extracted, second biggest one, and so on and so forth. Okay, that's one way to do sorting using a heap. Okay, so what's the time? What's the time? So this one, fast build heap is On, okay, no problem. So I have a for loop that goes from 1 to n, so the for loop runs On time. Okay, this extract max, in the worst, O log n, right? Correct? So is it then On log n? No. No. Correct lah, it is still On log n for this one. Okay. How? Okay, the exact analysis is something like this. The first time you extract max, it must be log n, correct? Because there are n items. Correct? In the worst case, I extract the first one, I put the leaf there, it shifts all the way down, right? So it's log n, correct? The second time, I have one item less, right? So it becomes what? N minus 1, right? And second time, third time, n minus 2, right? And so on and so forth. Correct? So this is actually what? If you know your logarithm, n minus 1 times n minus 2 minus 2 times all the way d1, which is what? Log of n factorial. What is log of n factorial? This is yet another identity. It's called Stirling's approximation. It gives you n log n. Yeah. Okay, so now after going through this, you know that you need a bit lah, not a lot lah. Okay, a bit of these kind of identities. Okay, so go and Google this up and then just memorize a few of them, and you should be fine. Okay, for this course. Okay, Ken? Yeah. So yeah, heap sort. Unfortunately, we cannot beat the magical big O of n log n barrier. Okay, for comparison-based sorting, because heap sort is also another kind of comparison-based sorting. Okay. Okay. So, okay, this one's done. Okay, heap sort. Yeah, created by this guy, John William Joseph Williams. Okay, let's quickly look at the Java implementation that comes together with your lecture notes. Okay, so just very quickly. Okay, so this is the Java implementation. Okay, so I have a binary heap class. Okay, I have two variables, two attributes. Okay, one is basically your heap, which is an array list. Okay, which we use an array list, and then I have the binary heap size variable. Okay, so my constructor here I have a constructor for the binary heap. I just create the array list, and then I add a dummy value first, okay, at index 0. Okay, then I set binary heap size to be 0. Okay, so this is your constructor. Of course, I can also have another constructor where I pass in an array of inputs. Then I just call my create heap operation on it. Okay, so now what I want to draw your attention to is actually these 3 navigation operations. Okay, can you see it clearly? Okay, I hope you can see it. So you see that instead of using the standard I divided by 2, 2 times I plus 1, I'm actually using bit shift operations. Okay, because why? I divided by 2, right? I divided by 2 is basically just I shift to the right by 1. Okay, so that's bit shift operation. Okay, left of I, which is 2 times I, is basically just I shift to the left by 1. Okay, and then right is I shift to the left by 1 plus 1. Okay, and bit shift operations are much faster than your mathematical operations, divide times, which is why we choose this formula, because we have a fast way of implementing it. Okay. Then you have your shift up operation, which is just a very direct implementation from the pseudocode given in lecture notes. Okay, then you have your insert operation. So, okay, in your insert operation, first thing, increase your binary heap size, of course. Then you check whether your binary heap size is bigger or equals to the size of your array list. If it is bigger, I need to call the add method. Okay, so add in the new key. Okay, otherwise, if my binary heap size is smaller than the size of my array list, then I just call set. Okay, go to index binary heap size, set the key to be, set the value there to be the key value. Okay, after that, I will call shift up on this index binary heap size. Okay, so the rest you can look at it yourself. Basically, they are just almost direct implementations from your slides. Okay. And then here you have a class which is the binary heap demo class, okay, which demonstrates the binary heap class. You can look at this, run it, okay, you can change it, okay, test it out yourself. Now, I've given you this code here, so you can basically use it for your PS, okay, for your PS1, but I want to make a disclaimer. This code here is for the purpose of demoing the operations on the binary heap. It's not meant to satisfy all possible inputs. Okay, so if you just copy this without knowing what's happening, copy it and then use it for PS1, you'll find that you might not pass some of the input test cases. So you need to know what's happening here. So I don't want you to just copy. Read it, understand what's happening, modify it accordingly for your PS. Okay? Okay, so let me go back to the slides. Okay, so let me talk a bit about PS1. Okay, PS1 is about the emergency room. Okay, I hope you never have to go to the emergency room, okay, of the hospital. But for me, because of my sickness, I often go to the emergency room. So the doctors there know me, they see me, oh, okay. Now, you know, in the emergency room, you have lots of housemen, right? So fresh grads from medical school. And then a lot of them, they are still greenhorns, so they don't really know what's happening. So when I go there, the doctor see me, he will just tell the houseman there, just do whatever he tells you to do. Okay. So I have more knowledge than them, okay, about my sickness. So you just, okay, do whatever he tells you to do. Okay. So, but that's not the point. Point is this. Okay, the emergency room, okay, is usually very, very busy. Okay, it's very busy. And you won't have enough doctors to see all the patients all at once, right? So you need to prioritize the patients, yeah? So usually before you go to the emergency room, you will be at the triage area and then they'll ask you questions like, okay, what's your pain level on a scale of 1 to 10, you know, and take your blood pressure and things like that. Tell me what discomfort do you feel and things like that. And then they will sort of rank your priority based on that. Okay, then once your rank, you'll be wheeled into the emergency room, and then the doctor will see you according to your priority. Okay? But this priority is, of course, not a static value. For example, someone might complain, I have a bit of chest pain and things like that, but then not very painful, just discomfort. Okay? Then the nurse will say, okay lah, maybe priority is low. Okay? Send into the emergency room. But then in the emergency room, suddenly, heart attack. Full-blown heart attack, what happens? You cannot say, okay, wait. You wait 5 more minutes, that's it. Right? So priority have to immediately change, right, to the highest priority, or the doctors will immediately attend to him. Okay? So that's what's happened. So that's what's happening in the emergency room. Okay? Okay, so for PS1 is like this. You are given a list of insanely many patients. Okay, insanely many patients. Okay, you have to prioritize the one who should be treated sooner over the one who should be treated later. Okay, so clearly it involves some kind of priority queue. Okay, so yeah, 3 subtasks. Okay, subtask A should be easy. Subtask A, you don't have insanely many patients, so small number of patients. Okay, subtask B, you might need to understand what's happening in lab demo 1 next week. Okay, or you probably don't need to. Okay, you can try it yourself. And subtask C is the challenge, because now you will introduce a new operation which I didn't describe here in the lecture. It's called the update key operation. So you have to implement this yourself. Okay? So, okay, this is your first PS. Okay, so that's it for this lecture. So please train on VisualAlgo on this topic. Okay, just go to VisualAlgo training, click on binary heap, set your question difficulty, number of questions, time limit. Okay, this link unfortunately don't work currently. Okay, it doesn't work. So yeah, just use this first method. Okay, doing training. And it only goes from easy to medium currently. Hard is not there yet, but it will be coming soon. Okay, so summary. For this lecture, we look at the heap data structure, its application as an efficient priority queue. Okay, we see the max heap. Okay, we see how to store it as a compact array, some of the operations on it, and how to build a max heap in OM time. Okay, and also a simple application of the heap, which is the heap sort. Okay, so you can revisit heaps on VisualAlgo. Okay, look at the e-lecture mode. Okay, to reinforce your understanding. Okay, so that's it for this lecture.